Today I'm just going to talk about three projects from my lab, and we study human hands, how the brain controls the movement of our body. So a little bit about myself. I joined UCF Mechanical and Aerospace Engineering and the Bionics cluster in 2018. So my lab is interdisciplinary. It's called Neuromechanical System Lab, which is located at Lake Nona campus. And we primarily study the neuro and mechanical principles underlying the control of human upper extremities. Because this is very interdisciplinary research, I do use different technologies. I will study human behavior, and we use robotics, so VR, and neural imaging to understand the behavior of human brain and human body. So in terms of teaching, I have primarily been teaching biomedical engineering courses. Just a special note here is I developed 2 new courses. So for BME, one is going to be available this fall. It's a modeling and simulation method in physiological systems. So basically, students gonna practice MATLAB and modeling simulation techniques. And the other course is it's called Methods in Neural-Machine Interface. It's going to come out next semester. So both of these courses are not limited to mechanical engineering students. And if your students wants to take a look at these courses, please ask them to contact me so I can give them a little bit of what they need to be in these classes. Okay, so in terms of my lab, so why do we study human hands? Well, human hands is basically a manifestation of intelligence, and so it has this unparalleled versatility to perform all kinds of tasks in daily living. And it's really not, we don't understand it, how it works, and because it's very complex, has a lot of many joints and muscles, and if you look at the cortical somatotopic representation of the areas which are designated to either receive sensory information or control muscles in the hand, are disproportionately larger than other body parts. So this means that there's a lot of information processing going on, and we don't really know how we can control this complex tool of our body so effortlessly, and there's no real machine that can match the capability of our hands. And not going beyond the simple sensory motor control, there's also involving a complex network of behavior in the brain that involves cognition of the memory. So we study all kind of hand behavior. So grasping, manipulation, one hand, two hands, or between two agents, human agents, or between a human agent and artificial agent. So there's all kind of behavior that involves hands. So from the application perspective, it's mostly the discovery of these research would go into health-related applications. So primarily the restoration of upper limb functions in different clinical populations. And for healthy people, so these can be used for maintaining and create enhancement for manual capability through exoskeletons or teleoperations. And ultimately, so if we learn enough about the neural control, we can potentially create intelligent machines that can replicate or go beyond what our hands can do. So I'm going to talk about 3 projects. So the first project is to understand cortical dynamics underlying the human hand, the interaction between the hand and object. So whenever we do some task with our hand, it's likely we're going to use a tool or grasp an object, right? So this process seems to be simple, whereas it started from looking at the object, looking at the properties of the object, where it is. And then you have to think about, okay, so what I'm going to do with it and what it affords what action it affords. So these involves and where, and also where the object is. So these involve different pathways in the brain that processes information to plan or organize behavior. For example, here, if you use your right hand to grasp this, you have to grasp the handle, right? And if you use left hand, you have likely to grasp the this cylindrical shape. So the forces and grasp configurations involved in different actions would likely to differ simply because you choose different hands to grasp the same object. So how does brain process information? Well, most of the knowledge comes from non-human primate research and a lot of behavior results. So our goal is to understand the spatial temporal features of cortical activity when we are doing this type of actions. So the approach we use here, we combine motion capture, which measures the behavior outcome or behavior feature of these actions, and then we use EEG to record cortical activities. And then we can use different objects for different actions or same objects for different actions. And then these are different conditions. And then we can measure the event-related potential, cortical potential or event-related spectral perturbation within EEG signals. And then we can classify them based on different actions and different conditions. So if you have a higher classification rates, it's basically saying that also there is some discriminative features in cortical activity that encodes certain aspect of this information. For example, this object, do I reach to the right side or to the left side? And if I reach to the right side, do I touch it or do I lift it? What action do I do? And these different conditions can be detected through these classifiers. And then, so this is from the engineering perspective, and then we can also look at other source localization techniques to find out the brain regions responsible for each of these tasks. And the future direction for this project is to understand, so to go from a healthy population to stroke patients, so that we can develop motor imagery-based rehabilitation tools. And we are also currently developing exoskeletons such that these actions of exoskeletons can be controlled by these brain-machine interface. So the second project is about motor learning. So basically, learning motor behavior is critical in the process of rehabilitation. Meaning that when if you have impaired motor function, the way to recover is to induce neuroplasticity through repetitive motor exercise in rehabilitation. However, for hand, it's quite difficult, and nobody really knows what type of exercise or repetition should be used to increase the dosage or to be more effective that can generalize to different activities. This is because our hand is so versatile and you cannot possibly train them to perform all tasks in your daily life. And you have to choose certain type of training such that you hope that this training can generalize to different, to other untrained tasks. So this project is currently funded by the National Institute of Aging, and we're primarily looking at healthy adult, and we compare between young adult and old adult. So the way we do it is we have different type of hand exercises. It could be producing a motion, producing a force, and also you can produce this motion or forces in different patterns. For example, it can be continuous and sustained forces versus very short, brief, ballistic type of actions. And we compare the result of this training and their effects on more complex tasks. So we can create this very novel dynamic task that requires you to use your hand to interact with two robots. And you can be controlling a pendulum or controlling a moving cursor that's subject to perturbations. So in all of these ways, we can understand how the sensory motor learning principle works in hand exercises. So the last project I'm going to talk about is related to prosthesis. I think I'm running out of time, so I'm going to go through this quickly. So we're using virtual reality to create this assessment environment so that we can test all kind of control approach and mechanical design of prosthesis. And we also use large-scale simulation because this environment is basically physics-based, so you can create a lot of dynamic evaluations of certain grasp behavior and see whether a prosthetic hand is reliable enough to grasp all kinds of objects. And then you can proceed to optimize the design of the control and mechanical aspects. And then we also investigate the different type of sensory feedback, because sensory feedback is important to interact with physical interaction between the prosthesis and environment. So we look at visual and haptic different type of feedback approaches, and we compare their performance. So in a VR-based environment. So potential collaborations, because I'm coming from a very interdisciplinary background, so I'm actually open to all kind of possible collaborations. So in terms of VR, it's obviously very useful in training and rehabilitation. We can have this, we can extend the VR environment we already have to a more clinical setting. We are also interested in tracking hand and object interactions naturally without any markers or any other wearable devices. In terms of robotics, we're interested in human-robot physical collaboration and teleoperation. And I'm also open to other type of neuroimaging techniques, such as fMRI and other neurostimulation to investigate the neural control of the hand. From material science perspective, a lot of these new prostheses could benefit from flexible sensing and actuation components, and that's definitely a hot direction of research. And also, I'm looking for clinical partnerships so that I can test these theories in different clinical populations. So I'm just going to finish right here. This is my collaborators and my students.